Hello guys, so this is question number 9 of Civil Services Mains Examination 2002, and it is a question of second law of thermodynamics. It is of 20 marks question. So let us read the question. A reversible heat engine absorbs heat energy from a source of hot gases whose temperature is falling linearly from T1 to T2. The engines reject heat to a constant temperature sink at T naught, assuming that any reversible cycle can be considered to be equivalent to an infinite number of Carnot cycles, prove that the maximum efficiency attainable for this heat engine is this expression. So let us begin. Now first let us make a diagram for this. So this is a source at temperature T. Now from this source a heat dq is given out to Carnot engine, and from this heat dq2. So let us sum this as dq1, and this is dq2, and this is sink at a temperature T naught. So the temperature is reducing linearly. So let us make a diagram for this also. So on y-axis T and on x-axis time. So it is linear decrement, so a straight line. Now this is temperature T1 and this is temperature T naught. This is T2 and this is some part of this line. Now consider this Carnot engine as it is shown in this figure. Now we assume that the source is at temperature T and the temperature changes by dt while doing some work dw. So some temperature change dt is shown by this. Now the heat extracted from the source by the engine, that is dq1, can be given by mass flow rate multiplied by Cp multiplied by temperature change, or let us write it at dt. Now efficiency of the Carnot engine, efficiency of Carnot engine is given by 1 minus T0 divided by T, that is the 1 minus sink temperature divided by source temperature. So work done by engine is given as efficiency into the rate of change from the source. So W is given by this. It is a small work, so dW. Now putting on the values, we get dW is equals to 1 minus T naught by T multiplied by m dot Cp into dt. Now we have got the expression of work. Now with this differential expression, if we integrate, then we can get the total work done. So integrating from T1 to T2, we get integration T1 to T2 1 minus T naught by T multiplied by m dot Cp dt. Hence W max is equals to m dot Cp into T2 minus T1 minus T naught ln T2 by T1. Now we have got the value of work max, and similarly total heat extracted from the source can be calculated. So total heat extracted from source is given as Q1 is equals to T1 to T2 mCp dt. This comes out to be m dot Cp multiplied by T2 minus T1. Now for minimum efficiency, therefore minimum efficiency is given by W max divided by Q source. Now putting on the values, this shows m dot Cp into T2 minus T1 minus T naught ln T2 by T1 divided by m dot Cp into T2 minus T1. If we solve this expression, we get 1 minus T naught by T1 minus T2 ln T1 by T2. Now this is the expression that is mentioned in the question, hence proved. So let us write here, hence proved. So guys, this was the solution of this question. Thanks for watching. See